Welcome to Circuit Valley. I'm Gaurav. This video is going to be the second video in the series of video where I demonstrate you how you can use oscilloscope to decode. As I have suggested in my last video, I'm going to make a series of videos. I will decode every single protocol you can imagine, and this video is going to be about I2C. You can see again same three oscilloscope being set up. On the right you can see RTB2004 from Rode & Schwarz, a 300 MHz 2.5 gigasample per second oscilloscope. This oscilloscope has 4 analog and 16 digital channels, and we are going to use both analog and digital channel in this video. In the middle you can see the behemoth of oscilloscope MSO S804A from Keysight. This oscilloscope is exceptionally 8 GHz, not 800 MHz, 8 GHz with 20 gigasample per second, and it also has 16 digital and 4 analog channel. You can see it has 3 probes already connected and the digital probe connected. Probes itself are 1158A 4 GHz probe, 1152A 2.5 GHz probe, and 1152A 2.5 GHz probe. All the probes except for digital probe are active probes. Even though not necessary for this experiment, all the probes are active probe and they are capable of exceptional bandwidths. On the left side, in the bottom, you can see my trusty old MDO3000, MDO3054, a 500 MHz oscilloscope with 2.5 gigasample per second. To help me generating all these signals, I'll be using a really interesting board. I'll show you in a minute how does the board looks and how does it behave. So let's take a look at the setup and we will show you. This is how all the probes are connected. They are all connected to this green PCB in the middle. So just to take a closer look at the board, the slow signals start from here, and you see that there is a SS clock, DAC output, I2C clock, I2C data, and on the right side, maybe I'll remove some of the oscilloscope probe. There is a SPI clock, SPI slave select, SPI MOSI, and on this little header you again have all the signals combined. These are the DAC, raw DAC data, digital values. On this side you have high speed signals, for example MIPI, or you also have USB LS, USB FS, and you also have USB HS. Probing a USB HS is going to be interesting. We will need 2 probes because I do not have any differential probe, so we'll learn about the probing as well, how to deal with a situation where you need differential probe and you don't have it. So our oscilloscope will help us. Only my 8 GHz oscilloscope can decode USB HS, and these normal USB speeds my MDO3000 can also decode. RTB2004 cannot decode USB at all. So I2C lines are in this corner. You can see I2C data and I2C clock. At the moment all the oscilloscopes are connected, and all the oscilloscopes are connected to these I2C lines with the ground connected on the left side and the right side. So let's take a look how to first of all set up a decode, or how to first of all set up a signal acquisition for I2C. All 3 oscilloscopes are currently connected to the same signal, and they are all updating their displays in the default mode. I have not optimized them to capture a specific waveform or specific nothing, and they are all just capturing and trying to find an edge trigger and a most optimal trigger for this situation. So let's get started, and I'll show you first how to set up a trigger and how to clean up this waveform, this jittering thing, and then we will take a look how to set up a decode, because currently even if you set up a decode will work, but it will be too slow or unreasonably flickering to be able to find anything useful. So let's go to the RTB2004 first. So let's do a quick comparison. This is the RTB2004, and this fast it is updating. And let's look at Keysight, and it is updating something like this. And if you want to compare, let's put both of them in the same window. I cannot judge who's updating faster, but I can show you there's one guy who's updating real fast. So this is my MDO3000, and you can see how fast its update displays. So first of all, to clean up the waveform, we're supposed to set up a trigger, and I'll show you how to deal with this waveform. So in this situation, this flickering of the waveform can easily be solved by a basic trigger. You don't necessarily need to go all the way length to find out the protocol and try to decode a bus and set up a bus trigger. We will try to find out a basic situation, and we will try trigger on this basic condition. Let's set up go to the trigger menu, and we will do a width trigger, and to be able to figure out the parameter for width trigger, let's let it run and maybe do a single capture. Okay, and we captured something. Let's do one more single capture so that we can see some packets. Now we see some packets. So we're supposed to capture somewhere, we're supposed to trigger somewhere like this. So you will see I'm moving both of these cursors and I'm measuring the pulse width on the clock line. It is around 800 microseconds, 886 microseconds. I'm going to set up my trigger in such a way that it looks for this specific pulse, and it's a positive going pulse. So I'll set a positive going pulse. And now we're supposed to set appropriate timing parameters for it. So when pulse is greater than, we will set like maybe 700 microseconds, not 70 microseconds, 700 microseconds. Okay, and now it should trigger stably. Okay, now we have other trouble, but definitely trigger is more stable now. It definitely finds something, and we need to find out what's the packet content. And okay, so we have packet in a packet. So these small packets, these repetitive burst of packets, they are consist of a bigger packet. So if you want, right now we are triggering on something like this in between somewhere, and many of such situations occur. So we're supposed to trigger something like that, start of the packet. So we'll try to set up a trigger on start of a packet. So it is around 9 milliseconds. So we will change our trigger condition to greater than maybe 8 milliseconds or 9 milliseconds, 8 milliseconds. Now let it run. Now it should do absolutely stable capture. We are in auto mode, so we change it to normal mode, and for some reason it cannot find any triggers condition. I will set it right actually. I'll do a force trigger, single capture, and measure one more time just in case I measured something wrong. So something like that. Okay, so it's still correct. Maybe I measured last time wrong. Let it run one more time. Force trigger. Okay, so these bursts, in between them there's a time of around, I think I was reading here, I was supposed to read here. So delta is 2 milliseconds, not 8 milliseconds. This is one gotcha. So we will set it to 2 milliseconds. Now it should trigger stably. Yeah, so it's pretty stable. You see it's triggering constantly, and you do not see signal flickering or going all the way haywire. There is one, because these packets are not repetitive, there is still some kind of anomaly. We will find out what that thing is, and how we will try to trigger on that as well, if that's what our concern is. We can also certainly, if you do single capture, and we can also look for packets, something like that, that is specifically triggers on that within the boundary. But for right now, it's good enough situation for us, or a good enough a signal. We will start decoding it, try to make sense out of it. After that, I'll show you how to set up a bus trigger on this to avoid this kind of weird situation where even though you have a decent repetitive trigger condition, but it's not that repetitive. There are some still stuff or quirks which need to be covered or need to be handled in such a way that it gives us a solid trigger. So let's zoom in. You see, this is some kind of start of a packet, and we don't know nothing about this bus other than this is clock and this is data. And let's have two packets, and I'll set up a decode. I'll use my mouse and go to the protocol menu. We don't need SPI, we need I2C, and we will configure it. Clock is channel 1 and data is channel number 3. Find threshold 1.8 volts, perfectly fine. So threshold, you can see this line appears to be denoting the trigger point, and let's turn on the bus. Okay, so this starts with 00 and it started to do this. I'll zoom in and I'll show you what does it do. Okay, so it starts with 00, trying to write, and for some reason there is no acknowledgement coming. I don't know, this, for some reason there is no acknowledgement. This is the board. It's supposed to behave the way it should behave. Maybe it's emulating NAC condition. If you want, I can show you in the bus table that there was no acknowledgement. So it says NAC. It appears to be the feature of the board itself. We'll go and look at this packet and we'll see there is state OK means acknowledgement came. So this thing you need to watch out in the I2C. It's not SPI. There is a, even though it's writing, it always have a bit coming back. So this is the next packet or the next write cycle. So you can see this is the device address, right? It says WA. On the cursor number 1, it says WA. It means it's a write cycle, and it says 50H, 50 hexadecimal, write, and green means acknowledge came. So both try to write something to the I2C device address number 50 and acknowledgement came. And if you follow closely, I'll maybe move the channel away from it and maybe make it smaller. You can see with the bus display we also have this waveform display. This waveform is denoting exactly what the decoder is taking the data to process. If you have thresholds wrong, this is to determine if you got your thresholds right. If you got thresholds wrong, then this small signal which looks like clock, it is a representative of the clock itself, then it will not look like a clock. And it will be different. Maybe you set the threshold too low, then you will have too many pulses. If you set the threshold too high, then you have no activity at all. So this way you can determine if your decoder is being fed the correct data. You are not in the state of garbage in, garbage out. So let's go further. I'll take the cursor and go further. You see this is the acknowledgement on the last edge. The signal was not high. So data got acknowledged, or write operation or the address got acknowledged. And then it wrote 00. Generally it's an address. If you're trying to write, then you write 00. And there's a, I believe this is this condition which you see, this is a small arrow. This is a restart condition. And it's again trying to read from this, read 50 and data 10. So this is a typical read operation from I2C device. You first send I2C device address, write the register you want to read, the address of that particular register, and then in the next operation after sending restart and sending the address one more time, you read the value. So whatever was there on the register number 0 on the I2C peripheral is being read with the data word 10. For some reason our master, whoever the host was, decided to not acknowledge this data, so you see this small red there and this small green there. This oscilloscope is quite modern. It tells you exactly what happens, and if you want we can take a look at the bus table and we will see that this is our first packet which is not being displayed on the screen, and this write operation happened. ID was 50, device ID or the chip ID was 50, length was only 1, it wrote 0, this is the 0, and then it read 10, and this is the 10. There is another packet coming maybe later on which is not being displayed there, and you will see, maybe I'll zoom out and you will see the same stuff. Let's zoom out a bit. So this is that 5012, and after that you got 5014 and bus display in the case of displaying everything. So you see there are many things, and this is how it got displayed. So it's very easy to decode I2C. And now we will try to set up a bus trigger, and we will trigger on a specific data instead of triggering on a start of the packet or the pulse. We will try to find out why this package is this which you see there. Right now we do not have enough memory, so you will see many knock knack knack. So this is also you need to watch. If you do not have enough memory in the oscilloscope, or you do not capturing small enough signal, then your decoder will not work very properly. Signal is still okay. If I zoom in, it will start decoding and these problems will disappear. Okay, but if I zoom out, my acquisition memory is very low. So I have set it to automatic mode and it's 1.5 meg. So maybe let's set it to 10 meg and we will see if it does better. And I'll do a single shot capture. Okay, and you can see now I will zoom in and show you how good of a signal quality we have. There are many knacks. There may be real knacks, maybe some quirks. Maybe let's zoom in right here. So it's a good enough signal. These are real decodes and you really have these many knacks coming here and there. We can also select here in this oscilloscope, and this oscilloscope also tells you where you are in the selection memory. We zoom in. Okay, so we can select the bus packet and it automatically jumps to that area. This is the zoomed view, the whole packet view, and this is this. That's so you see this cursor, moving around, this rosa or pink looking thing. So when you click somewhere, it automatically tells you where are you pointing. So I'm pointing to this packet 5000501, and this is what 50001 selected on the bottom list, and this pink cursor moves around when I change the selection on the screen, and this is what it's telling, that you are pointing to this particular address. So we are supposed to set up a bus trigger. We will find out the criteria for bus trigger, and then we will set up the bus trigger. Close this bus window and get out of the zoom view as well. I want to first find out what is going on there, where you have this problem of this not repetitive prop packet. So it's supposed to come here where my first cursor is sometimes come here and disappears. Let's do one more single capture. It came. Now we'll go in there, we will take a look what's the content. I'll just zoom in and we will move my zoom window right where the packet is, and you will be able to see it. So this packet looks like it says 7A, 7B, 7C, 7A, 7B, 7C, 7A, 7B, 7C. So on the device number 54, let's see if we have other device 54 somewhere. So okay, so this is a different thing. I do not know if it is appropriate or not. This appears to be longer address, but we can definitely trigger on this guy 54H, and first is does a read is represented by this yellow color, and then it does write. So we will set up a bus trigger on this exact condition and we'll try to trigger only on this condition, and then you will most likely see that we have a different view because this packet is also not that repetitive. Maybe we will get a stable trigger, maybe not. We will find out. Trigger, and we will do, instead of width, we will do serial bus trigger, and this I2C trigger gives you many options. You can trigger on start, stop, restart, no ACK, address and data. We're supposed to trigger on address and data, and not any address. We need hexadecimal 54 54. Okay, and data should be, let's remove it, 7A. So we'll do 7A. Okay, byte offset 0, it's perfectly fine. Now it should do bus trigger. I will zoom out. I'll let it run. So wunderbar. Now we are doing a data trigger on a specific address and a specific data. Remember that packet, and this T is representing our trigger point. Exactly when it detects 547A, it triggers. And let's zoom out. Let's see if this is a stable trigger. It appears to be a stable trigger, at least more stable than the previous trigger. The waveform is still flickering a bit, but it's still a better trigger condition appears to be rather than just triggering at a pulse. So this is how you deal with the I2C signals, or you deal with the I2C packet and trigger condition with bus trigger, and you deal with the advanced trigger condition where you need to specifically trigger on a specific thing. Let's look at those weird addresses which we saw before, and let me zoom in if they are intentional, or they may be like 10-bit address. I2C also supports a larger bit addresses. Yeah, so this is what they are. This 153, it appears to be a 10-bit address. So I think that's enough for RTB2004. Now I will move to my Tektronix MDO3000, and we will see if MDO3000 can also handle this 10-bit addresses and also handle these weird bus trigger conditions or pulse trigger condition and how the signal stabilizes there. So let's start on this. Right now it's set to H trigger. I'll do a single capture. Same stuff. You will exactly see the same packet because they are both probing the same signal. The view on this oscilloscope is a little bit different. Okay, so now we will try to find out the trigger condition same way, the way we did it. Here you're supposed to find out the cursor menu, and then you will be able to, what do you call it, you will be able to measure and then set up a trigger. Here there is no touch screen available, so I look for this gap. As you remember, it was 2.46 milliseconds or something like that, 2.5 milliseconds. So I'll set up my trigger to be width trigger or pulse trigger on 2.5 milliseconds, and we will see how it goes from there. Pulse width, I need a positive going pulse. Threshold is 2.6 volt. I believe the threshold need to be set a little bit lower. We need to change the channel as well for the threshold. Now threshold need to be 2.9 volts. I believe it's okay. Positive going pulse when greater than 2.2 milliseconds. So I'll now let it run, and let's set the trigger to the middle. So it's triggering, but you see it is very stable. Same with the RTB2004. But it's not that stable. You still see this fast flickering of those additional packets. So our job is to find out if we can, with this oscilloscope alone, find out a better trigger condition so that we can look at the other packets as well. So first we will decode the bus, and we will go in there and see if we can decode it. So we need to activate the P1, and right now it's set to I2C. SPI will set it to I2C. We'll define inputs, and clock is on channel 1, data is on channel 2. That's perfect. Threshold, we can set the threshold somewhere in the middle of the waveform. So that's correct. That is also correct. Everything is fine, and you see it is decoding. The whole bus is getting decoded. Address 0 is being written and it's not being acknowledged. Let's go into the next packet. Go to the next packet. Maybe I'll capture a little bit bigger and we can use the zoom feature of this oscilloscope. Zoom in, and I think we are too far off. Now we are correct. Okay, so remember the second packet was 54 and 1010. So now the bus display, you set this include read write address. If you include it, then it will be displayed differently, and if you do not include it, it will be displayed differently. So this thing you need to watch out for. Not every oscilloscope displays these quirky things same way, and this is always an argument if the read write bit is included or not included. And this is one little feature of one little problem which you have always in the oscilloscope, that if that thing is included or not included. Our other oscilloscope also showed the same thing, data 50-50 and write to 50 and 50 and then read from 50 address, and the rate data was 10. You can see this oscilloscope memory and its acquisition bandwidth, and if I show you how much we are acquiring, record length is 10K. I can increase the record length and you will see the waveform will clear up a bit and look more beautiful. If you decrease the length, it's not decodable. So this thing you need to watch always, how much deep you are decoding or encoding. This oscilloscope allows you to set up to 10 meg. When this oscilloscope was released, 10 meg memory was a massive memory. Generally I deal with 10K or 100K, and that's good enough for these kind of low buses or low speed buses, or not that important of a buses. So we see that data is appropriate, and less packet is going to be 12, read 50, 12. So exactly the same which we decoded on the other oscilloscope. Let's zoom out a bit and we will try to capture that weird packet which arrives sometimes only. Okay, so we'll do a single capture so that we can find out its trigger condition. We may need to increase the acquisition memory to 10 meg because that's what maximum our oscilloscope allows, and we will single capture one more time. It will take some time. You see it down there, this arrow is rotating, bus not yet computed. So because oscilloscope takes some time on 10 mega sample to be able to decode the memory, I'll zoom in this time as well, and we will look for that weird package which doesn't get repeated all that often. So we are here and it says 186767, and we will trigger on that and we will see how does it look in the trigger and if it stabilizes the trigger as we did it with RTB2004. But it appears to be a different packet because remember the address was different. And you look at it, that this oscilloscope in the 10-bit mode can detect address 153 as was with our RTB2004 as well. Okay, but I believe, I'm not sure because 10-bit address is not normally you deal with. So you see that exclamation mark, if you remember it. See that exclamation mark? This is right there because it's supposed to detect this exclamation mark. I'll show you with the cursor. This exclamation mark, it is overlaid on the top of W, even though it can handle 10-bit addresses. It appears to be that detection mechanism for ACK on NAC has failed and there is a small bug in the oscilloscope. So not every oscilloscope is same. That's why we are using 3 different oscilloscopes to verify the same information. And that's why you see that little bug-like condition there. So address is being displayed there, data is being displayed. I believe, let's find out why it does the data look different or data value is different than my RTB2004. Maybe bus display, hex, that was also hex, and this is also hex, but that was different address. Maybe we are looking at different things or different bus or different data, but it doesn't matter. We will trigger it there. Trigger condition instead of pulse width will go to trigger one more time, bus trigger, yeah. So we'll trigger on I2C, trigger on address and data. So address supposed to be 18. Supposed to be, I cannot use my keyboard, so I need to enter it like this. Okay, 18 hexadecimal, and data is supposed to be 67. Okay, now let it trigger and we'll see if it does trigger here. I'll zoom out, maybe remove the 10 mega sample memory to 100k so that it can decode faster, and I'll set the trigger in the middle, and you see it's exactly triggering the way other oscilloscope was triggering on a different data, and it has absolutely stabilized my signal. And there are some still quirks, and the other packet which is supposed to be at 54787B, this is not being displayed here because it's a different data, I believe. So with the MDO3000 also we were able to find the appropriate trigger condition with the bus, and I believe that's it for this oscilloscope. And we will move to my MSO, MSOS804A, the Keysight 8 GHz oscilloscope, and we will see how does it look there. So you can see it looks no different because the trigger is not appropriate. So waveform is all flickering on the screen, and we have only 2 channels connected, so there is no activity on the other bus. If you want, I can enable the digital channel as well, so that you can see that the same bus is being detected on the digital channels as well. Let's enable only the first channels, and disable everything else. I think they are still connected to I2C to SPI. Yeah, this is connected to SPI. I'll change them on the board. So now we have it, digital and both analog channels, they are connected to the I2C. Let's do a single capture so that we can look at it a little bit better. Yeah, same stuff, nothing special, same I2C signal. Let's set up a trigger, let it run, and we will set up a trigger. Same stuff, positive going pulses around 2 milliseconds. Setup, pulse trigger, positive going pulse around 2 nanoseconds. And I want to be greater than 2 nanoseconds. This has a sequential trigger as well. If you want, you can set more triggers, and after pulse width it will detect the edge and stuff like that. There's a lot of stuff going on in that, but for that matter is right now it's okay. I think the level is okay. We'll find out soon. And this trigger is currently auto. We need to have it triggered, and let me set the level. Is it better? It's definitely not better in any way. And we are triggering on positive pulse, going positive. Okay, so when greater than 2 milliseconds, not nanoseconds. Yeah, now we see a solid trigger. Same stuff, some packets arrive and disappear. So this is the packet which you saw on the RTB2004, which was displayed at 547A7B, and on the other oscilloscope it was displayed at address 18, because they may most likely be two different packets, and we can definitely trigger on the both of the packets if needed. But right now we are only concerned about the packet which we're seeing. And let's set up a decode. First of all, we set up a decode, then we will see rest of the things. Let's zoom in a bit, and I'll show you. Setup. Protocol decode is already I2C, and you see 7 or 10 bit address, and it also has 8 and 11 bit address, but read write bit is included in that. And data is on channel 2, clock is on channel 1, and let's turn on, see if it detects something. Can't perform decode invalid data because we have lost one signal. Clock or data is lost. Oh no, we have it, but channel number not 2, channel number 3. Okay, so we have it. Now we have it. Address 00, this is what we saw last time. If you zoom out, the next address is going to be, which we saw, 50 and 01. So you see down there, address 00, address 50, data is 0010. Same as we found on the RTB2004, and the same as we found on our MDO3000. It's nothing different. Let's zoom out a bit. Next packet was 5012. We have 5012, and this oscilloscope, of course, it is a oscilloscope with a normal computer. It can, in this area, it will really shine and give you a lot of data to deal with. And this bus table is almost by default available, so you can look at the whole data, and it gives you these tree views, that which physical address, which physical data path, and where the data went. Maybe stop it for a second. So you can analyze every single packet, which address, 153 hex, NAC, ACK, everything can be analyzed, can be exported. This is the advantage of having a fancy oscilloscope, or an oscilloscope with a lot more. Okay, we are interested in that weird packet, so we'll try to set up a data trigger in this oscilloscope as well, so that we can get ourselves familiarized with how to set up a data trigger. First of all, you need to find out that data. You remember, after 153, there's supposed to be this. Let's zoom out, and I'll do one more single capture. Now we see the packet. You see, this is the packet, and I'm supposed to find out what that packet is. It must be somewhere here. Okay, so you see that marker moved there, and if I move it somewhere else, it will move somewhere else. 00 packet is always first, so marker moved at 0, and now this marker is at this packet. So we are having address 18 as displayed by MDO3000. Data is 676869. Okay. Somewhere down the line there will be other packet as well. Let's find out if there's other packet we can also look for. I'll do single capture. Okay, and do we see it? We don't see it. I'll see one more single capture. We are interested in 7A, 7B, 7C. Yeah, now we see it. So this 7A, 7B, 7C packet also came. So this is the same packet. Sometimes it sends 7A, 7B, 7C with the address 54, and sometimes this guy sends 18, 67, 68, 69. So this is the board which is sending, and we were able to determine with just few clicks or few press of the buttons and 2-3 times single capture. And as our trigger is stable, it does capture sometimes these stuff, and we can set up other trigger. Let's see setup and gauge timeout protocol trigger, and I want to see I2C trigger. Setup, channel this, channel that. Instead of start, 7-bit address supposed to be 54. Enter. Data should be 7A. Okay, enter. So of course this oscilloscope is more gruntier, so it allows you quite a bit of data. Other oscilloscopes allow you only like 3-4 bytes worth of data. You can even set more trigger, acknowledgement or not acknowledgement. So there is a bigger oscilloscope, provides you better trigger conditions. So now we are set up appropriately, and see 7-4. Now see 54, 7A, 7B. That's where we are triggering. We are triggering in the middle of the packet, on that rare packet which rarely comes. And if I am right, on the next packet you will see something else. I'll do a single capture, and we will try to look here. What is here going on? Okay. So next packet may be different. So you see, you have this packet. So one time board sends 676869, and next time they are alternating between two different type of pattern. One time it will send 676869, and another time it sends 7A, 7B, 7C. So these packets are alternate. This is the 7A, 7B packet, and this is 676869 packet. So we got our oscilloscopes ready, and we set them up for the appropriate trigger conditions, and everything looks wonderful. Everything is set up. You can see this is a fancy oscilloscope, shows you a lot more details, and I think that's it for this video. And you can visit my website www.circuitvery.com. If you have any protocol in mind which I can show you decoding with this oscilloscope, this oscilloscope can decode almost every protocol, then please let me know, drop a comment, and I'll make a video about it. There's a next video coming about another protocol soon.